Okay, this is Physics 1A, 1617 for April the 8th. Today we're going to be talking about this problem that's right here, as well as talking about coefficient of restitution. So let's get to it. In this problem, we have a proton collides elastically with another proton that's initially at rest. The incoming proton has an initial speed of, we'll write this down right here, once I get the pen. So initial speed, we're going to call that speed just v initial, and that's equal to 3.5 times 10 to the 5th meters per second. It makes a glancing collision, as shown. There's a figure, but we're going to draw our own figure. At close separations, the protons exert a repulsive electrostatic force on each other. After the collision, one of the protons moves off at an angle of 37 degrees to the original direction of motion, and the second deflects through an angle phi. We want to find the final speeds of the two protons. So the picture we would have here would be like, we start off with one proton right here, and it's moving along a straight line. So it's moving to the right with this initial velocity that we called v naught up there. Can I just try a little bit to draw a bit of a straighter line? That's a little bit better. So this is the initial velocity of v initial like this. There's another proton that's sitting over here at rest, and when this one makes its way over here, this proton ends up right here, and it makes a glancing collision where the angle that it makes after it goes off of it, it's kind of like, think of it like a pool ball. Like pool ball comes in and then they collide, and what do? They go off kind of at an angle, right? And so let's say that it moves off at this thing right here, and that it makes an angle here that we can call, this is 37 degrees, but we're going to call this theta, and just say up here that the angle theta is equal to 37 degrees, so I don't have to write 37 degrees all over the place. The other one moves off at a different angle, so this one moves off, and then we need a little bit of a... This one moves off at another angle, and I'm going to draw it down like that, where this... Here, let's draw that line a little bit longer. Okay. This one makes an angle phi, right here. Oof. Phi. We don't know what phi is. That's one of the things that we're going to have to calculate in this problem. And we don't know the velocity of each of these objects here. So I'm going to call the velocities here v1 and v2. Okay, so we defined what v1 is, what v2 is, and what the angle is, the unknown angle. This is a little different from a problem we did yesterday for a couple reasons. First of all, because this is a proton-proton collision that involves the electrostatic force. The electrostatic force makes it so that the protons never touch each other, which means this is a special type of a collision. This is what we call the elastic collision, which means that kinetic energy is conserved. Okay? It's an elastic collision. The collision we worked with last time was two objects colliding in this way, except at the end the question was, is it elastic? And we found out that it wasn't. So the fact that we now know that it's an elastic collision is going to give us one extra equation we can use, which means we can also solve for extra variables, basically, right? Because I think the problem we did yesterday, this velocity here was known, okay? But in this case, it's not. That's the main difference. And this type of problem is kind of tricky. So what I want you guys to do is to do the following. I want you to write down the equations you would use to solve this, and then attempt to solve them, okay? And I'll give you like a few minutes to write them down. The equations you're going to want to write down are, remember what we learned last time, is that if you sum up all of the momenta in the x direction before the collision, that those should be equal to summing up all of the momenta in the x direction after the collision, and then the same thing for the y direction, sum up all the momenta, the y components of the momenta initially, and that should be equal to the sum of all the y momentum in the final state. And then finally, you're going to do the same thing, but you're going to say sum up all of the kinetic energies initially, and we want to write equations for all three of these. So I want you guys to try to write these down. I'll give you a couple minutes to do so. And then we're going to verify you got them right, and then we're going to have you guys try to solve them. Okay? So take a couple minutes, write down each of those equations. Oh, and in case you don't remember, the definition of what momentum is the symbol p, and it's equal to mass times velocity. So really you're going to be saying px, for example, would be mass times the x component of the velocity, right? So anyway, give it a shot. Okay, was that enough time for you? Are you guys able to write down the equations? Okay, let's see if we can figure these out. So what did you guys get for the initial x momentum on the left-hand side here for this equation? Let's do this down here. All right, yep, so mass times v naught, that's right. And then for final momentum, okay, let's actually write this out in a way that you guys can read, though. So mass times v initial should be equal to. Now, I didn't say anything about their mass here, but they're all going to have the same mass, right? They're protons, right? So they all have exactly the same mass. Wait, do you guys know that? Is that something that... It would be reasonable to ask the question, how do I know that all protons have the same mass, or why do all protons have the same mass if you want to? But if you don't have that doubt, then we can just keep going. So this one's going to be like mv1 times what? Yeah, that's the x component of that velocity, so that's the x component of the momentum. And then we get the same thing for the other one, except it has, what is it, cosine phi, right? Just a different angle. Okay, all right, then we've got this one. I think we're just going to start it. We can put this one, I want these to kind of line up, though. Okay, use a different color for this one. Okay, what about this one then? What's the initial momentum in the y direction? 0, because, well, basically I didn't say it, but we're making this the x direction, right? We're making that the y direction. Okay, so, man, these lines look really straight sometimes. If I could figure out how to do that, then it'd be great. Okay, so 0 equals, and then the final momentum is going to be something like this too, right? So it's going to be m v1, but we just put sine theta in here, and then plus m v2, and then sine phi. Now, you could put a minus sign here if you want to. It would just affect the sign on phi, okay? So it's up to you whether you put a minus sign there. My personal opinion is you should always just make everything positive, but it's up to you. Okay, so then this one, kinetic energy. Maybe start this one just a little bit up here. So for this equation, now we just need the, kinetic energy, which is just 1/2. Put this one in black too. This is going to be 1/2. That's the initial kinetic energy. And then the final kinetic energy is just the sum of the 1/2 mv squareds for the final situation. Okay. So does anyone have any questions about those? Hopefully you guys were all able to get the same equations. Okay, so now what I want you to do, and this might take a little bit of time, I want you to actually try to solve these equations. Okay? The variables that we're looking for are v1, v2, and then phi, right? Those are the things we don't know. So I want you to do your best to try to solve these equations. And I'm rewriting them. I'll rewrite this one a little bit differently. I'm just canceling out the m's, right? For now. That's all I'm going to do. And I want you guys to try to solve these equations. Okay? This one, we're going to remove the halves and the m's, right? This one just says v naught, oops. V initial squared equals v1 squared plus v2 squared. Okay, try to solve them. I'll give you guys like 5 minutes, okay? And then at 2:20, we will solve it together. And if you have any questions or ideas, let me know. I make any mistakes when I wrote all those out? You have a question, Coeff? You're saying this sign right here, Coeff? Why is that not minus? So yeah, you can do it either way. The angle here, since it's a sine, like we're just gonna get a negative angle basically, is the reason why. so it doesn't matter. But if you want to, you can put a minus sign in there. Yeah. Does that answer your question? Because like the sign of, whoops. Sine is an odd function, so it'll work out. I know that it looks bad. This plus this equals 0. Maybe that bothers you guys. It used to bother me, but I don't know. I got over it, I guess. Okay, that was about 5 minutes. Do anyone have any luck? Anyone get an answer? If so, tell us what you did. If you weren't able to get an answer, maybe you tell us why it was hard. I can give you the mass. It's not important because it's already canceled out of all the equations, right? But m is the mass of the proton, right? It would be the proton mass. But that isn't going to help you. You're still working on getting phi. I tried using substitution for V2. How did that go, Kenny? Yeah. Mm-hmm. The x equation. Just call it the x equation. Yeah, this one. Yeah. And how'd that go? Did you try using this equation then? No. I'm saying, yeah, if you sub this one in for here, right? You also then need to take something else and sub it in over to the other equation, right? Does that make sense? Anybody else get close to an answer or know like a good strategy for doing this, at least?
Well, I got v2 squared in terms of v naught and the signs of the angles.
Mm-hmm.
But I'm just now solving for the angles.
You can sub for v1 and v2 into the third equation. You guys want to try that real quick? All right, let's see if we can do it. All right, let's see. So this equation tells us what I'm doing this fast because I'm going to tell you right now we're going to have to try another method. Maybe it'll work. I don't know. So v2 is equal to what? Negative v1 sine theta divided by sine phi, and we take that and we put it over here. So v naught is equal to v1 cos theta plus. So v2 would be negative v1 sine theta. And then cos phi divides sine phi. And now we have an equation that just has v1, but it also has this other unknown, which is the phi. But we could technically solve for v1 now and say, okay, well, v1 now is equal to what? V naught divided by cos theta. This is going to be a long, complicated expression. I apologize for that. Minus sine theta. And then I think that cosine over sine is cotangent, right? Cotangent phi. So I think you get something like that. So, okay, now we know what this is in terms of phi. So now we say, okay, now we got to get all these things together up into this equation here. Well, that's going to suck because now it's like v naught squared equals, I got to square this whole thing now. Oh my god. This is awful. This is getting to be horrifically complicated, isn't it? There's a theta there. There's a theta there. There's a cotangent. I apologize I'm going fast. There's a reason I'm going fast because I know for a fact this is going to be, it's atrocious. You can all already tell, right? And be like, oh, now this is v1. Well, holy shit, v1 is, I'm sorry for cursing. v1 is this whole thing. Oh my god, I've got to do it again. I've got to square that same thing again. And Jesus, and now it's like you're squaring out this thing that's going to have a cotangent phi, and it's going to have cotangent phi squared, and you're going to get the same. Can you guys see this doesn't work, right? It just actually doesn't work. Or if it does work, you're going to have to plug it into Wolfram Alpha at the end. At that point, you might as well just plug the original equations into Wolfram Alpha and have it solve for you anyway, right? So this is not the method. This doesn't work. The normal substitution method will leave you with pages and pages of algebra, and at the end of the day, you're going to plug it into a computer algebra system like Wolfram Alpha. So, yeah, that doesn't work. But there is a way to do this. The thing that's tricky is the fact that these are squared here, but they're not here, okay? So really what you need to do is you need to square some things, okay? You need to square some things in order to, you need to square some things in order to fix this real quick. Let's fix these up real quick. So here's what we're going to do. There's kind of a trick for how you solve these, and this is the trick. You want to get the v1s together, first of all. So we're going to do v naught minus v1 cosine theta on this side, and say that's equal to v2 cos phi. Okay, so all I did there was I just moved that term right here to the left-hand side of the equation. This one is already good to go. Okay, so now here's what we're going to do. We're going to square this equation. We're going to square this equation, like both sides. So the left-hand side of this equation is going to be this thing squared, okay? That's going to be v naught squared minus 2 v naught v1 cos theta minus, or plus v1 squared cos squared theta. And then the right-hand side is v2 squared cos squared phi. Hopefully I didn't go through that too fast, but the left-hand side is basically, let me make it more clear what we're doing here. We're squaring that thing, right? So when you square that, it's a binomial, so you get v naught squared, you get plus v1 cos squared cos theta squared, and you get the cross term here, which is a 2 in front of it because you get 2 of them, okay? When we square this equation here, let's go back to green so we can identify the difference between these two. This one just becomes v1 squared sine squared theta is equal to v2 squared sine squared phi. And what we're going to do next is we're going to take this equation, If I can do it. I don't know if I'll be able to do it, though. I probably can't. Can I just pick it up? Almost. I think it's going to be missing some things. That's not a good idea to do it then. So we'll just rewrite it. Or I can't really copy it. So we're just going to rewrite this one below this, and we're going to add the two equations together. How about we do it like this? Equation 1. Equation 2. Nah, it's going to look worse if I do that, I think. I'll just stack add them. So the left-hand side here, we just need to... Actually, you know what I should do? I'm being stubborn for some reason. I should just take that one and put it here. That'll work. There we go. Now we want to add these two equations together. Okay, not the one above it. Okay, but just the... Let's just demark it with the blue line. So everything below this we want to add together, right? So what are we going to get? On the left-hand side, what's up? Okay, I'm noticing people are saying things. I would not have gotten that. So when in doubt, square it. I mean, I don't... It's because they're squared over here. And I'm saying that this is just a technique for solving problems like this in particular. You know, there's always different techniques for different problems, so this happens to work pretty well in this case. I will say, in regards to your comment, when in doubt, square it, I would say never be afraid to try new things, right? In mathematics, there are all kinds of things you can do to equations that may simplify the problem. Never be afraid to try new things, is what I'm trying to say. You know, sometimes you take the derivative of both sides of the equation, and that helps you out. Sometimes you square both sides. Sometimes you take the natural log of both sides, right? There's all kinds of different things you need to be comfortable with doing if you want to be strong with your mathematics. So look what happens if you do this. This is pretty cool. So now, it's pretty cool. It's not even remotely cool. It's incredibly nerdy, but there's nothing wrong with that. So it's cosine squared phi. Oops. This becomes cosine squared phi plus sine squared phi, right? And so now you've just eliminated a variable, right? Because this is equal to... Oh, it does still break up? I wonder if part of it's sensitivity. You think it's sensitivity, or is it like a straight up dropping of the audio? What if I just make my sensitivity stupidly low? That'll probably work, actually. It's much better than it used to be, though. That's good to know. Okay, I basically made it so my sensitivity is going to pick up every single sound in my house, but hopefully we're good. Okay, because I did notice my voice was cutting in and out there, and it may have been that. Okay, left-hand side of the equation. Sorry to interrupt, but you're recording the class. I'm unable to see the stream due to tech. Absolutely, yes, I'm recording the class, and it will be put up onto Discord, to YouTube, and I'll type that out just so. Yeah, it'll be up on YouTube basically about 5 or 10 minutes after the class is over. It'll be up on YouTube. Okay, so let's keep going with this because we're limited on time here. Left-hand side of the equation now has become v naught squared minus 2 v naught v1 cos theta, and then again on the left-hand side we have something similar happening where you've got v1 squared here and here, and then you just get cos squared theta plus sine squared theta. Let's move down a little bit as we keep solving this equation. So there's our equation, but the great thing is now these are like this is equal to 1, right? It's the one identity everybody can remember. This is also equal to 1. So what we're left with now is v naught squared minus 2 v naught v1. Ooh, I got a little kind of bad there. v1 plus v1 squared equals v2 squared. And now we can use our other equation. Now we can take this guy and we can actually make use of it. Let's just move a copy of it down here. I copied all the little dots too, it's funny. So that's our other equation, right? So this one we can rewrite then as what, like, we can pick whatever we want to solve for here. I'm going to solve for v2, let's say. So v2 squared, right, is equal to v naught squared minus v1 squared. I forgot a cos theta, you're right. That's absolutely right. Let's make some room for that and slip that in there. Forgot the cos theta. Thank you guys for noticing. Very much appreciated. Okay, that's the one. Check 2v. These look good. Yeah, okay. So there we go. And we rearrange this one, the kinetic energy equation, like this. And now we can just replace over here. So we're going to get v naught squared minus 2 v naught v1 cos theta plus v1 squared equals The really nice part about this is you might think that we may have to solve a quadratic now because you've got your v1 to the first power, your v1 to the 0 power, and your v1 squared, but oh, maybe we will have to solve a quadratic. I thought it was going to cancel out, but it looks like it shows up as the opposite sign over here. Making sure I did my math right. Looks right. So what we end up getting, oh, that's what cancels out. It's the other one that cancels out. Yep, it's the v1 to the 0 term that cancels out, actually, because those show up on both sides. There we go. So now we end up getting our equation that we can actually solve. We add the v1 over here, so we're going to end up getting 2v1 squared minus 2v0 v1 cos theta equal to 0. You factor a v1 out. You can factor a 2 out if you want to, too. And you'll get v1 minus 2v0 cos theta. Wait a minute. Have I messed this up? Yeah, we know theta, right? That's the one given. It's the only known in the problem is that this is 37 degrees and that v0 is equal to, like, what was it, like 3.5 or something? Yeah, 3.5. It's like, this problem's weird because I forgot, like, which things are actually unknown. But there we go, 10 to the 5 meters per second. Okay, so we know those two variables, so now we can actually solve, and we'll put this in a different color for the final solution. So we now know that basically either v1 is equal to 0, we know that's not the answer, or the other thing is equal to 0, so v1 minus 2 v0 cos theta is equal to 0, so basically v1 now is equal to 2 v0 cos theta, which means it's equal to 2 times 3.5 times 10 to the 5th times cosine of 37 degrees, and I think cosine of 37 degrees is something like 4 over 5, so 8 over 5 times 7 over 2. $56 over 10, so it's going to be something like, no, that can't be right. What? Oh, there's no 2. You're right. That's right. I was thinking this answer, this 2's gone. That 2's gone too. Thank you for figuring that out. There, that 2's gone. Ah, so instead of this, it's just 3.5 times cosine 37, right? So that would be 7. 3.5 is 7 over 2, and we're multiplying by 4 over 5, so that's 2.8, I think, right? So it's going to be, oops. I think the answer is going to be 2.8 times 10 to the 5 meters per second. And that's the answer for what V1 is, and we can use this to solve for all the other things now, too. Okay, do you guys have any questions? Any questions at all? I really like these problems. If you can't tell by my enthusiasm with which I'm solving it, I really, really think these are cool. And it's a particle physics problem. It's a particle physics problem. So these are the kind of problems that I would solve all the time when I was in grad school. So that's kind of the way you do these things. Let's solve for the rest of them. So this equation tells us how to find V2, right? So then V2 is going to be equal to the square root of V0, which was 3.5 squared, minus V1, which is 2.8 squared. And then this times 10 to the 5. So this one's going to be equal to, can't do that one in my head. Maybe we could. They're both multiples of 7. So it's like 5 squared plus 4 squared. Oh, so it's actually, wait, we actually can do this in our head. It's like, no, it's going to be like the square root of 7 times, that's not easy. It's the square root of 7 times 3 or something like that. I don't know what the square root of 7 is off the top of my head. So this is going to be 2.1. Oh, it's not the square root of 7 because it's squared. Right. So it's 3 times 7, which is 21. We could have done that one in our heads. Oh well. Oh well. All right, so there's your answer. That's V2. And if we want to find phi, we're going to have to go back to like maybe that equation right there when it's not squared. So I think what sine inverse of negative V1 sine theta divided by V2 should give us our answer here. So V1 is 2.8 divided by V2 is 2.1, and then times the sine. Ooh, I left out the sine inverse part of this. So it's sine inverse of negative 2.8 over 2.1 times sine of 37 degrees. I'm almost certain that this is going to come out to be 53 degrees. Happens to be the case that if you have equal mass particles, okay, and they engage in an elastic collision, that phi plus theta, the angle between them, always will add up to 90 degrees. This only works in elastic collisions, though, and it has to be same mass. It's elastic, same mass. Can you imagine how much shorter this problem would have been if we could have just simply said this from the beginning? We never would have had to do all the other tricks that we did. If we already knew what phi was, we could have used this equation alone to solve for, not this one. We wouldn't have needed a third equation, basically, is the idea. Right, so check that. Does that actually give you 53 degrees? 2.8 over 2.1 is 4 over 3. This is pretty easy to see. 4 over 3, and sine of 37 is 3 over 5, so you end up getting 4 over 5, which is 53, yeah. Okay, there you go. Your book doesn't have any problems like this in the text, but it does in the homework. So I took one from a different textbook, because this textbook has... this other textbook I used, by the way, and I really encourage you guys to seek out other sources, but this is the other textbook that I'm always using. This is the textbook that I taught from for years when I was at Marymount, and it's just flat out, in my opinion, and I'm kind of biased, I think it's a better textbook. So if you're looking for something to read on your own time, especially during the quarantine where you just, I don't know, you're not getting the normal kind of teaching you would, go get a copy of this book, you know, somehow. You can see that I downloaded a PDF, right? So, I mean, I know you guys are very capable of doing that. In fact, I'd be happy to share this with you. I don't think this file has any viruses, but if you want me to share it with you, I could. So, good textbook, really good textbook. Much simpler explanations, much better examples. You want access to that file? Can I just share it here? Is there anything? Am I gonna get in trouble? I just be like plus and just pop this in here. Like I don't think I'm gonna get in trouble like at all, right? So, I mean, desktop. I'm just gonna delete this message, but for now, if you guys wanna go ahead and click on this link, no one's gonna notice. What? I mean, Inky314 on Discord posted a message to a private server that hardly anyone has access to. I think we're fine. Oh, on YouTube?
Yeah.
Like, you know how many people watch these videos? Like, nobody watches these videos, dude. Nobody watches these videos. Right? Yep. No ad revenue for whiteboards of physics explanations. Anyway, there you go. It's processing, but it should be up soon. Now, that book, seriously, it's really good. And it's not only good for 1A, it's even better for 1B and 1C and 1D. Like, I promise you. It has way more information, way better problems. I've been trying for years to get them to change it, but, you know, people be, you know, stubborn. I don't want change. Stuck in the past, yeah. Okay, we have 20 more minutes, so I want to talk about coefficient of restitution. I want to do this problem. I don't know that we'll have time to do this problem, but, I mean, we technically do. I just trying to... Well, it's lecture time ends, and then it becomes lab time, which, like, yeah. This is the problem we're going to do here, okay? But we're going to do a little setup for it, because we need to talk about this topic of coefficient of restitution. So what is this? You take a bouncy ball and you drop it on a surface like concrete, let's say. It bounces pretty high, right? You take a piece of Play-Doh and you drop it on a surface. It doesn't bounce at all, right? What's the difference between those two objects? Well, one is springier. It has more bounciness to it, and that's what coefficient of restitution basically means. It means bounciness, okay? Bounciness is a very scientific term. How bouncy something can be. And in the case of, you know, a perfect collision, the coefficient of restitution would be 1. And this number basically is going to be a number that we'll use the symbol E for, and it's going to be between 0 and 1, although I think it can be greater than 1 in certain cases as well. with special like billiard balls and stuff like this. Okay, but it's a coefficient, so it varies between these values, and this is basically how it's defined. So say you have a surface, right, and you drop a ball from some height above that surface. I could have sworn I picked up the blue one, but there it goes. We drop that ball from some height above the surface, and we call this height like maybe h1 or something like that. And the ball falls, right, and right before it hits the ground, it picks up some speed, and then it bounces back up, right? So right before it impacts the ground, it's going to be moving downwards with some speed. And then right after impact, it's going to start bouncing, it's going to bounce upwards, right? So it's going to go back up with some speed. And we'll call that speed v2. And then let's say it bounces to a smaller height here, and we'll call that height just h, okay? So it doesn't bounce quite to the same height, although if the surface was perfectly springy, then it would bounce to the same height, right? There's some amount of energy that gets kind of transferred somewhere down here. Maybe it gets absorbed in terms of internal energy in the ball. Maybe the ball deforms. In the case of Play-Doh, right, what would happen? The Play-Doh would just splat on the ground, right? It would just go splat, and it wouldn't bounce at all, right? That's the extreme case, right? But if it's like, let's say you drop a rock on top of concrete, it's going to bounce a little bit, right? You drop a rubber ball on top of concrete, it's going to bounce pretty high, and that's kind of the idea right here. So we'll call this one, we saw in the blue pen, yeah. We'll call this one H2. So what's the relationship between all these variables? Well, we can say that in the case of what's going on the left-hand side before the bounce happens, that you have an energy conversion process that happens, right? Where you start off with some potential energy, mg times h1, and it all gets converted, we assume, into kinetic energy, like that. And so you can get a little bit of a relationship here that h1 basically, right, is equal to the square root, no, not h1, sorry. My bad. V1 is equal to the square root of 2gh1. And then you get the same thing in the secondary case here, where you have an energy conversion, except now you start off with kinetic energy, right? And it gets converted into potential energy. So again, we get this relationship that V2 ends up being related to the square root of 2 times g times h2, right? And now if we find a ratio of V2 divided by V1, all right, and really we're talking kind of about absolute values here of the vectors, just the magnitudes. We don't care about the direction here. You're going to get something like the square root of 2gh2, and you're dividing that by the square root of 2gh1, right? And so you end up getting that these are related to each other as the square root of h2 over h1. And this is one definition of what the coefficient of restitution is. You drop something from one height, that looks like an N, sorry about that. You drop something from one height, it bounces, and then it bounces up to a different height, and that's the square root. If they were equal to each other, the coefficient of restitution would be 1. If this height was 1/4 of this height down here, then, you know, if you called this 4 and you called this one 1, then the coefficient of restitution would be, I guess, a half, right? So that's what it is. Now, the way that this affects problems is that now we can have a way to describe how inelastic a collision could be, okay? Like, how inelastic is it? Oh, well, this symbol tells you it's a 0.5 inelasticity or something like that. For a perfectly elastic collision, the coefficient of restitution would be 1, like the one we just talked about here. And I'm going to give you another equation that you can use with this too. We learned last time that in a perfectly elastic one-dimensional collision, that there was this relationship that we could write down. And I always have a hard time remembering it, so I remember it like this. If I take the velocity of an object before a collision plus the velocity after the collision, it should be equal to the velocity of the other object before the collision plus the velocity of the other object after the collision. And then this ends up getting rewritten like this. V1 minus V2 is equal to V2 prime minus V1 prime. And then we rewrote it again by putting a minus sign on the outside right here. And we said we're going to write it so that you can see that there's this overall change in the relative velocity between the two objects, right? Well, it turns out that this same equation right here, we can modify it just a little bit more. And we can put a new term inside of here, okay? It's on this side, right? Looking at my notes. What are my notes? Yep. So this is what our equation can become. So if we instead make it so that the velocities here represent the component of the velocity perpendicular to the surface. And the way we'll do that is we're just going to do like this. We're going to put a little perpendicular sign down here, a little perpendicular sign down here, and we'll see where this shows up. And then if we put the E right here, this actually gives us a much more general expression. This is actually in your notes. The impulse momentum packet, it's at the top. It's one of the equations you start with right there. And specifically what it says is that this equation is only good in the direction perpendicular to the surface of contact, okay? And just to give you an example of what this means, where's that other problem at? There's a problem where this is going to come in useful. This one here. Well, we will probably not do this today, but this is a good example of where this comes into play. So the way this equation works is you've got your v1 and your v2 are your initial velocities, right? And your v1 prime and your v2 prime are your final velocities. Now this object is a ball that hits off of the Earth, okay? This is the Earth down here. So the way that this problem works out is the ball bounces and it bounces off like this, okay? And what happens is that v2 is basically 0 and v2 prime is basically 0, okay? But what this equation tells us that we can do here is we can relate the final velocity perpendicular component to the initial velocity perpendicular component as long as we know the coefficient of restitution. You have a lab manual problem like this, and we probably won't get to it today. We'll talk about this next time. Yeah, so that equation is used for these kind of problems, and we'll get to that. This is just the theory. The application, I think, will make you understand this more, but the perpendicular component in this case would just be the y component. This would be the y direction. That would also be the perpendicular direction. God, that looks like a function or something, so I don't want to do that. The y direction or the perpendicular to the surface of contact, this equation is true, okay? And that would be true as well if you're talking, for example, about two billiard balls. If you've got a billiard ball here and you've got a billiard ball here, perpendicular to the surface of contact means that's the surface, right? So the perpendicular direction would be like this. God, that looks awful. Sorry. Perpendicular to the surface of contact would be a line that would run like that way. God. If I turn the thing sideways, it's so hard to draw a diagonal straight line. That would be perpendicular. That's better. That's the perpendicular direction, okay? That's what that means, basically, okay? So, you'd have your x components and you'd have your y components, and this basically just tells you how you need to align your coordinate system. So let's look at how this can be used to solve a problem, okay? This is going to be the equation we're going to use, but we're going to do a one-dimensional problem first because it often, helps to start off with something simple. Plus, this problem is genuinely very cool. All right, so a ball is dropped from a height h. We're going to change this. I don't like the notation here. I didn't write this problem, but a ball is dropped from a height capital H and it rebounds to a height little h. Find the coefficient of restitution E and find the time that it takes to stop bouncing. Okay, so I'm sure all taken maybe like a tennis ball or something. You drop it from some height, it bounces, 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 and eventually it stops bouncing, right? This problem answers the question, like, how long does it take? How long does it actually take to stop bouncing? So this is our setup, and I'm going to change the setup for the problem. What I'm going to do is we're not going to call this one, I got to go to the regular marker to erase, right? Yep. We're not going to, it won't even let me erase it because it's a picture. That's fine. We'll just redraw it. So here's our surface, and our ball starts, let's say, right here, and it's going to fall down, and then it's going to bounce up again. So it's going to bounce, and we're just going to draw it bouncing kind of like it's done in the picture. Let's call the very first height h naught, okay? Now the ball is going to bounce, so it's going to come up to some new height up here, and then it's going to fall down again, and then it's going to bounce, and then it's going to fall down again, and it's going to bounce. That should be enough to indicate what we want to indicate. And we're just going to call each of these heights different heights. So this is going to be h1, this is going to be h2, and this is going to be h3, and we'll just indicate that with little lines. And then subsequent bounces will be h4, etc. These look like n's. I apologize. These should be h's. Okay? That's our setup. And all we really know is that we're supposed to find the coefficient of restitution. We've already done that. Okay, this is really what we're going to do. So the coefficient of restitution is basically just equal to the square root of the less height over the small height, right? So h1 divided by h naught. Okay, that's your coefficient of restitution. God, these h's, I'm making it look like n's. I apologize. h1, h2, 0. There we go. That's our coefficient of restitution, right? It's also worth mentioning that the coefficient of restitution in this case should also be equal to any of the subsequent height jumps, right? So if we also do like h2 over h1, or if we do h3 over h2, any of these represents what the coefficient of restitution is. That's important. Okay, first things first, how do I figure out the time that it takes to fall the first time? Anyone know? Kinematic equation. We know the initial velocity is 0. We know delta y is like h naught. We know acceleration is g, right? So we can say that if we want to find the time, we can use one of our kinematic equations. We'll start with the one that says 0 is equal, not 0. Delta y is equal to vy initial times t plus 1/2 ay t squared, but the initial is 0, so this becomes 2 delta y divided by g is equal to t, and if we take a square root, that's what we got. But we know what delta y is actually, so we can replace delta y with h naught. That would be, we'll call that t naught, let's say, right? But then what's going to happen is that it's going to have to go from here back up again and then fall down again, which will take double the time, right? Not this time, but if we call the time intervals like, so t naught is basically just the first fall, right? If we say t1 is the time to go up and down, and then that t2 is the time to go up and down, and t3 is the time to go up and down, we could say, well, t1 would be equal to double this, right? But we'd have to replace the height. That's all we gotta replace. It's just h1, right? You guys follow that? Do you guys agree? Cool. So, if we take the total time now, this is going to be something like t naught plus t1 plus t2. And we know that this is equal to that. And I did stop talking there because I was just focusing on making it look somewhat good. Plus dot dot dot, right? Does anyone have any questions?
So when we double it, we have to replace the height.
Well, sure, because the time that it would take for this ball from rest to fall down to the ground would be 2h1 over g square root. And then the time to get up there would be the same, right? So it's the up and down motion that we're considering for each of these. That's why we have to double it. We could have started off with this ball on the ground. We throw it up to some height if we wanted to, and then every one of them would have the exact same term. But we didn't do that, and that's fine. So now the next thing to do is to factor out kind of the common things that are going on here. And specifically what I'm going to factor out, because we're kind of limited on time here, I would have you guys actually work on this problem yourself. We're going to factor out the very first term from everything. So the first term is going to become 1. The second term is going to become square root of h1 divided by h naught. The third term is going to become the square root of h2 divided by h naught. And we're even going to write in the third. Oh, that was awful. Let's just fix it. Why did it have to be h's? h2 divided by h0 plus, and we'll write one more term in here, h3 divided by h0 plus dot dot dot. Now we can replace these because we know that this first term right here, I'll scroll back up just a little bit, we said that this was true. We know the coefficient of the first term here is actually equal to e, right? And it allows us to solve something here too. This is going to go a little faster than I probably should, but if I square both sides of this equation here, then I can say that h naught is actually equal to, let's do the steps. Let's just do the steps so I don't go too fast here, because I'm very much capable of doing that very quickly. Okay, so this equation, if we square both sides, will be e squared is equal to h1 over h0. So then h0 is equal to e squared multiplied by h1. And we can continue this process for the second equation. We would get h1 is equal to, I think, e squared times h2, and h3 is equal to e squared times h4. Wait, it's 0 to 1. h1 is equal to e squared h2, and then, oh, the last one's h2. I got it backwards, my bad. This one should be h2, and this one should be h1. Yep.
Where did the twos go?
Oh, you're right. I got this completely wrong. The twos? Oh, I dropped the twos too. I'll fix that like this. 2 here, a 2 here, and a 2 here, right? Those ones? Yeah, I probably should have factored those out too, but that's fine. Did I do this wrong? Man, I'm going way too fast, aren't I? Yeah, because the h naught would multiply over here and get divided. So you're absolutely right. All of these are wrong. These are all wrong. Not completely wrong, but wrong enough that let's just write them again. Thanks for noticing that, Ash. Okay, this actually says, yeah, this is the more interesting thing. h1 is equal to e squared h naught, and then h2 is equal to e squared h1, but h1 is equal to e squared, so you get e to the 4th. h naught for this guy. h3 is going to be e to the 6th. h naught. h4 then would be, we don't have it, but e to the 8th, not h naught. There we go. That look right to you guys? Because then we can actually plug this stuff in here. h2 over h naught is equal to e to the 4th. But you're taking the square root, so you're going to get something like this. Plus 2 e squared plus 2 e cubed plus 2 e to the 4th. Can you guys see that? Oh. Does that look okay to everybody? Okay. So the goal here was to figure out the time that it takes to stop bouncing, right? And we're actually going to pick some numbers here. We're going to let e be equal to 3/4, and we're going to let h naught be equal to 1 meter, and then obviously g is going to be 9.8. My question would be, what's the answer then? Do you know how to solve this one? Yeah, it's the fastest anyone's ever figured that out. Usually people take a while to see it, but you're right. I don't know if it's the fastest. People usually figure it out pretty quickly. This is a geometric series, right? And when you have this sum right here, I think the first term needs to be 1, doesn't it? Don't you want the first term to be 1? So what I want to do... What's up? Here, let's look up on the internet for people that don't know what we're talking about. So the... Yeah, I think you need to start at 1. But if it's 1, it's like 1 over 1 minus the ratio, right? So a geometric series is basically a series where you have something like this, a half plus a fourth plus an eighth plus a 16th. And the way that you solve it is you say that if this is your sum, where is the term? Here it is, right here. Yeah, when a is equal to 1. So if you have a series where it's like 1 plus r squared plus r to the third, etc., this whole thing is equal to 1 over 1 minus r. So we do need the first term to be 1. So let's fix that real quick here. That's easy to do. All we need to do is to factor out the e from that expression. So we're going to have, turn over your pen. We're going to have 1 plus, we'll have 2e, and then that's multiplied by 1 plus e squared plus ... And then this entire thing here reduces down to something pretty simple. This whole thing is just going to become 1 divided by 1 minus e, as long as e has to be between 0 and 1. It can even be negative? I don't know about that.
Yeah.
It can be, right? Can't it be like negative a half and it still works?
Yeah, it could be negative
that whole thing becomes that. That's multiplied by 2e plus 1. And then all of that times square root. And let's just really quickly calculate what the answer is. So it's going to bounce an infinite number of times, but it's eventually going to stop bouncing, right? And whatever that means. It's not really going to bounce an infinite number of times. It's just going to eventually bounce until the point when it's no longer really... so we're going to get, what is it going to be? Square root of 2 times 1. This is the total time to stop bouncing, by the way, to keep track of what we were actually doing. So it's all of that, right, multiplied by 1 plus 2e. So 2e is going to be 2 times 3 over 4. And then that is multiplied by 1 over 1 minus 3 over 4. Which this is going to be what? 1 minus, this is going to be 4. And that's going to cancel as 1 minus 6. Whoa, that didn't look good. Oh, it's not minus, it's plus, right? Does that look right? Let's see. 1 over 1 minus 3/4 is a quarter. 1 over that is 4, which cancels out with that. 1 plus 6, so you get something like 7 times the square root of 2 times 1 meter divided by 9.8. Does that look right to you guys? I put it in my calculator just to make sure. 1 divided by 1 minus 0.75. Negative 1 times 2 times 3 divided by 4 plus 1. And then we do the square root thing. So square root of 2 over 9.8. No. Square root 2 divided by 9.8. And then that is multiplied by 7. So the answer is about 3.16 seconds. About 3 seconds. Negative bouncing, it bounces through the earth and ends up on the other side and in some type of a upside down world. All right, do you guys have any questions? Do you guys like that problem? Did I go through it too fast? Do you guys have any questions? Do you guys have any questions? Cal 2 knowledge? Since it's been a while since you've seen a series? Oh, Ash is saying, yeah, it's a little bit fast. Yeah, the recording will help. Yeah, you can go back through it and watch it in slow-mo and pause and all that kind of stuff. It's Calc 2 knowledge for sure. You forgot all of Calc 2. Yeah, series is one of the hardest things in Calc 2, but this is a series that I have to be careful about how I say this kind of stuff. I left a parenthesis off of here. It's a series that you may have seen in like an early textbook or something like that. I don't know. This particular geometric series is just one that's kind of famous because I don't know why, but it's just one of those things that comes up in a lot of math books I read when I was a kid. Are they all in this form, or do you always... No, it's just... The interesting thing about this problem, in a way, is like the fact that the geometric series pops out of it. Like, that's what's interesting about it, is that you don't always solve these things with geometric series. Like, the other problem we would do here, that I copied in over here, wherever it is, this one, for example, you don't use a geometric series for. It's just a straight-up coefficient of restitution problem. It's kind of boring, though. This one is one where you use this equation, but it's like a two-dimensional one, and we'll do them, but you don't always use a geometric series. Now, it just happens to pop out in this particular case, which is fascinating to people like me. Whether you guys think it's interesting or not, I don't know, but I love math. I always have, and this is cool. I'm going to stop the recording there.